So when we work in this fashion, the first one we're going to just see if we can work it out. So anybody notice the transformation that's happened here? Anybody see maybe something? Reflections, expansions, compressions, translations? Flipped on the x? Yeah, this graph would definitely have to go to the other side. Before it became the one over here. So there's definitely an x-axis reflection. Okay, anything else? There's definitely been some translations. Up one, yeah, definitely moved up one. And what do you think? What else? Let's move to the right. Yeah, 3 times. So that wasn't too bad. How many of you were looking at this red graph that I drew here to help you figure out the translations? Yeah, okay, so basically when we reconstruct a graph, that's what we're going to do is at each step we make a quick sketch to help us find the next one. So most people end up doing that automatically, but it's not obvious unless someone helps you the first time. So we could write this in as y equals negative f of x minus 3 plus 1 to get from this graph to the next one. Okay. So in the next example, oops, my apologies. I know I'm going a little quick today. But
is it still recording?
It is, yeah.
Oh.
Okay. So for the next example, we have to work like a detective kind of and go backwards. So if the person who went from this graph to this one did so, they would follow the same order that we did. So they would be following in this order like we did. So let's try and work backwards and figure out how they got there. So the first question is, are there any reflections?
Yes.
Right. So there is, and you can see that it's had to jump across the x-axis. So the first thing we're going to do is just make a sketch to show where the graph would be if that was the case. So it's going to be something like, oh, I don't know, something like this after the reflection. Okay. So it doesn't need to be perfect. It just needs, enough key points on there to help us figure out the next step. So when we go from this step to the next one, I'll do it in a different color. We need to figure out, have there been any expansions? And we might as well look for compressions at the same time. So what do you think? Has this graph been stretched at all? How so? How do you know 2? Well, one thing we can do is we can check and see where points have moved. So for example, if I go from here down to there, that has a height of about 6. If I go from here down to here, that height is about 3. So yes, you're correct. It is double. You can see that the graph has doubled in height. If we were to check in this side, this has a width of 4. This also has a width of 4. So there is no change horizontally, only vertical. So vertical stretch has changed. It's become 2. So what we want to do is we want to show that to help us find the next step. So if this was doubled, it would go like this. Something about like that. Now we have to figure out where the translations have moved this graph. And the easiest way to do that is pick one obvious point. So it could be anywhere on the graph that you see is obvious. Maybe I'll pick this point right here. Okay. I'm confident that that point is where it should be in this graph. Here's where it would end up when I'm done. So to get from here to there, the only translation that's happened is it's gone up by 3. Okay, so one piece at a time, a quick sketch on each of those to help me get to the next step. And I end up with y equals negative 2f x plus 3. Okay, so I'm going to let you guys take the next one all by yourself, see how you do with it. Remember, do draw the steps one step at a time, just to see how you're progressing. Okay, how do you get from the left graph to the right graph? Okay, so it looks like people are catching on to this. So the first thing I notice is that there is a reflection on the y-axis. So in red, I've drawn my reflection. So to keep track of this, okay, expansions and compressions. Well, again, if we do this little thing where we measure, okay, the graph is 5 units this way. It's 2.5 units here. So already I can see that there's been a horizontal change. This here is 4 units tall, while this here is still 4 units tall. So there was no vertical change. The only thing I've got is horizontal stretch factor equals 1/2. Okay. So I'm going to quickly sketch what that would look like. That means these points move in by 1/2. So if I move everybody in by 1/2, okay, so the projector is coming back on. There we go. So here would be my quick sketch of the 1/2, which takes me to about there. And finally, I have to pick a point. So maybe I pick this point right here. On that graph, it's moved up to there. So the translation is 3 up. So that gives me a final equation, y equals f of -2x plus 3. Okay. So the last thing that we need to talk about, and if the projector dies, we'll just go on to the whiteboard, but it's transforming an equation. So
Again now?
it is. We are recording, Anthony. So if we have an equation, remember that's the only time we're going to make use. Can somebody tell me, please, what's the most important thing to remember about this notation? Sum it up as simply as possible. Horizontal one side, vertical on the other. So we're going to start with what we know. If somebody was to tell us these facts about a graph, we're going to write up a function that's been transformed as such. Okay, so here's the what the function might look like. If we reflect it in the x-axis, vertical expansion, compression by 1/4, and we move it 4 units to the left and 3 units up. Okay. So hopefully at this point in our lesson, hopefully you'd be confident. I know I did that quickly. Again, I apologize today. We have to move a little quicker. Hopefully you're confident at taking this description and turning it into this function. Okay? Now we go from this to the key difference, which is all the vertical stuff goes to one side and the horizontal stays where it is. So vertical stuff, here's the vertical stuff. That's all affecting the graph vertically. So is that. So if I wanted to write this as a transformation notation, subtract 3 and then divide by -3. So everybody's been moved to the left, that's vertical. And the horizontal stays on the right. So the whole purpose of doing that is now it tells me that whatever was y has now become -1/3 y minus 3. And whatever is x is now 4x plus 4. Okay. So it's only really useful to us in transformation of equations. We wouldn't do this for graphs. I believe in Alberta they do this for all of the stuff, whether it's equations or graphs. I believe Alberta uses this notation for everything. Okay, so to finish the question off then, this is the, if you can get to this part, you got it beat. It's going to be replace y. So this y here becomes -1/3 y minus 3. Those x's become this part here. So 4 times 4x plus 4 minus root 4x plus 4. And I know you've been doing that kind of algebra for years now. I'm not going to ask you to expand it. You'll notice that if it was on the provincial exam, usually the multiple choice questions will leave it in this form, because that's what they want to know is, can you transform the equation? They're not as interested to see that you can do the algebra of it as well. Okay, but at this point, if we wanted to, we could reorganize it and we'd have an equation that's been transformed as described. So just to go over the process with you again, because you will see it when we do some review, if you haven't already encountered it in the workbooks, is first job is to come up with the transformation notation, or sorry, the function notation that we've already been doing. This should be what you're comfortable with. Then you're going to move all the vertical stuff to one side and leave the horizontal where they were. Then that tells you what to replace y with, what to replace x with, so that you can transform the equation.